You guys have heard of conservation laws, right? So you don't have to watch this video if you don't want to. This is from the Science Asylum as well, about a mathematician from the late 1800s, early 1900s named Emmy Noether, depending on how you say it. And her theorem, she's a mathematician, and this is the caliber of mathematician this woman was. Einstein and a guy named Dennis Hilbert, who was probably the greatest mathematician maybe of all time. They were trying to work out the kinks in general relativity, Einstein's theory of general relativity. There were a lot of issues with it that they couldn't resolve. And so they called this mathematician with pretty much no background in physics, and they said, can you help us with this? And she came along and she fixed it. She literally fixed the problems with relativity. Not only that, she proved why conservation laws actually exist from a mathematical perspective. So amazing. One of the smartest people ever in history. And so when you hear things like conservation of charge, which you learn about in chemistry, conservation of mass, conservation of momentum, which we'll learn about, conservation of energy, which we're going to talk about today, all of those conservation laws can be derived from observations of symmetries, what they call symmetries in the universe. I'm not talking like symmetry like one side of my face is symmetrical. I'm talking like more like time symmetries and space translational symmetries and weird things that you'll learn about if you major in physics. She proved that if there's some type of symmetry that exists in the universe, it leads directly to some kind of conservation law. And she used pure mathematics to do it. It's pretty amazing. I have looked at her work and no way I'll ever understand it. But I know what it means, and it's pretty cool. And I'm not going to show that video, but I would recommend watching it. One of it interesting. Dennis Hilbert did a series of lectures on the topics that she figured out, and he did the series of lectures because she wasn't allowed to, because this was early 1900s, and they wouldn't let a woman actually give lectures in university settings at that high a level. So she would guest lecture there, but really it was her show. They would just be advertised under Hilbert's name. So very interesting story. Very smart person. She was ousted by the Nazis right in the 30s, so she had to go through that crap as well. So it's a very, very interesting woman. I would definitely recommend looking her up if you have an interest in such things. Okay. So for the rest of the period, I'm going to talk about the history of all the energy in the universe. From the beginning. Okay. Let me zoom in here for the folks at home.
You can teach astronomy again.
Yeah, for a little bit. So you don't need to know most of all this, but I think it's interesting, and I think if you can actually understand what I go over here, some of it, then you'll gain an appreciation and an insight into the concept of energy that you might not otherwise. So at the beginning of the universe, there's an event that happened that we call the Big Bang that didn't look remotely anything like this. Not remotely. They say that the Big Bang... If you talk to a physicist, they'll describe the Big Bang as the moment that the universe actually came into being. It wasn't like space existed and then there was an explosion and a bunch of stuff flew out into it. Space itself was created at the same time as the mass that's within it. And that moment of creation is what we call the Big Bang. What happened at the instant? Nobody knows. There's a lot of ideas. Nobody knows. Nobody knows what happened before. There's a lot of ideas, but nobody really knows. We do know what happened a billionth of a billionth of a billionth of a billionth of a second after the Big Bang. We do know what was going on then. How do we know that? I'll talk about that in a minute. But just understand that when you see pictures like this illustrating the Big Bang, it's not remotely accurate. You really can't comprehend in our puny ape brains what really was going on at the moment of the Big Bang or immediately after the Big Bang. So it's just a useful tool that illustrators use when they try to show you pictures of the Big Bang. But like I said, we know what happened very shortly after the Big Bang happened. And so you're talking 10 to the negative 43rd seconds. We actually have an idea of what was going on in the universe. The universe is very small, even though it might have still been infinite, but that gets into stuff that we just don't want to talk about today. So early in the universe, it was very, very much smaller. Like all of the energy and matter was crammed into a much smaller volume. And so you had crazy high temperatures. We're talking 10 to the 30-some degrees. Crazy high temperatures. So most of the energy in the universe at this point was thermal. A lot of kinetic energy from photons that are moving around, photons of light. So it's just very hot, very dense, very non-conducive to life universe. But then it starts expanding. The universe has been expanding ever since it was created. And so as it expands, it starts to cool down. So after about, 10 to the negative 34th seconds, which is really still a very small amount of time, the temperature drops enough so that you end up having photons freely moving, not really freely moving, but moving around. And then you have the gauge bosons, which are the force mediator particles for the weak nuclear force that you might have learned about before. And then a little bit more time, still a fraction of a billionth of a second, still a little bit more time. And then you have the first protons. The first protons start to being formed. Oh, before those you had gluons too. Gluons are the force particles, mediator particles that dictate the strong nuclear force, which is what keeps nuclei together in atoms. But then things cool down enough so that the quarks, you guys have heard of quarks? Quarks are what make up protons and neutrons, and they do other stuff too, but every proton and neutron in the universe is made up of 3 quarks. The quarks can then, once the temperature goes down enough, the quarks can then start combining into the first protons and neutrons. And then after about 1 second, you have stable protons and neutrons, and you lose what are called the mesons, which there's still of some of them, but not quite as many. And then after about 3 minutes, things are cooling down. You don't have atoms yet because it's still way too hot for protons to actually grab onto electrons. But then after about, 300,000 years, now things have cooled off enough so that the first atoms can actually start forming. So the electrons aren't moving so fast because of their thermal energy. They slow down because things are cooling down so that protons can actually grab onto them and form the first hydrogen and helium atoms. No heavier elements at that time, because heavier elements, does anyone know where heavier elements are created? In stars. And so there's no stars yet. So there's no heavier elements other than hydrogen, maybe trace amounts of lithium, but no metals, no oxygen, no carbon, none of that stuff. And it wasn't until these first atoms formed that the universe actually became transparent. Before that, anytime a photon would be emitted by some kind of process, it would just immediately get absorbed by some of the radiative soup that it was sitting in, the quark, gluon, all these other particles would just immediately absorb it because there's just no space. There's no space. It's way too hot. Pressure's too high. But after the first atoms start forming, then things kind of condense out and the universe becomes transparent, and we can actually see the light from that time. We can see that light if we look far enough out into the universe now. So you get the first atoms, and then after about, and then the first stars follow shortly after, because all of these particles, all of these atoms have gravitational potential energy if they're in close proximity. Just like if I lift an object, I give it gravitational potential energy, I let go of it, it converts to kinetic energy. So these particles start collapsing into the first stars, and then those first stars start making the first galaxies. The first galaxies start popping up about 400 million years after the Big Bang. And then you let enough time go on, and about 15,000 million or 15 billion years later, here's the universe as we see it today. How do we know all this stuff? How do we know what was going on a billionth of a billionth of a billionth of a second after the Big Bang? Well, we can create conditions just like that right here on Earth in particle accelerators. Yeah, just on a much smaller scale. But we can create. First of all, particle physics makes predictions for what the universe should have been like at that time. And then we build particle accelerators, the largest of which is the Large Hadron Collider you might have heard about. And they crash subatomic particles together at near the speed of light, 99.9999% the speed of light, and they observe the conditions. And those conditions on a very small scale are exactly like they were at the beginning of the universe. The temperatures and the pressures that you see here, we can attain on the Earth just on a very small scale, and we see all this stuff. And so that's how we know that's what the early universe was like. This is the standard model of particle physics for those of you that are interested in that kind of thing. Particle physics, in my opinion, is like maybe the hardest thing to learn, to understand. It's just crazy. It's weird. It's really weird. It requires quantum mechanics to actually do. But these are all the particles in the universe. You got the 6 quarks. All of the neutrons and protons are made up of these quarks. You have the electron down here. It's a lepton type of particle called lepton. Then you got the neutrinos. You got the tau and the muon. You got the gauge bosons here. These two are the mediators for the weak nuclear force. The gluon is the force mediator for the strong nuclear force. The photon itself is what light is, but it's also the force-mediating particle for the electromagnetic force. The graviton is not here because the graviton has not been discovered yet. It is predicted, but it hasn't been discovered yet, so it's not on this particular picture. A lot of standard models show it because it's assumed to actually exist. We just haven't detected it yet. This guy right here, the Higgs boson, you might have heard of. It was first detected in your lifetime. It was about 9 or 10 years ago. They detected the Higgs boson in a particle accelerator collision. Interesting thing, it's named after a guy named Peter Higgs, who predicted the existence of that particle in the 1960s, and who was still alive when they actually detected it for the first time. And there's footage of him whenever he actually found it. He starts tearing up because it's pretty. How did he predict that? It's, again, way over my head. Particle physics is crazy. But the graviton probably also exists. It's a massless particle, and it's very low energy, and so it's probably very, very hard to detect. However, gravitational waves, they were just detected, I think, 3 years ago. 3 years ago, the first gravitational waves, Einstein predicted those in the early 1900s. Right? So the graviton probably exists. Anyway, you don't need to know that, obviously. This is another way of looking at the history of the universe. You have the Big Bang. And really, when most people talk about the Big Bang, what they're referring to is the inflationary epoch of the universe's history. There's a very small fraction of a billionth of a second time when the universe expanded much more rapidly than it ever has since. You have the cosmic dark ages where you have no light. Actually, the universe is not transparent. And then, galaxies, stars start to form, galaxies start to form. And then at this time, dark energy, you might have heard that term, dark energy is what's used to reference the expansion of the universe. The universe has been expanding since it started. Not only that, but we now know that it is accelerating in its expansion. So that's pretty interesting. People won Nobel Prizes for figuring that out. This is a cool picture. This is a cool picture. There's no stars in our galaxy in this picture. None of the stars in our galaxy are in this picture. These are, maybe that one. There's one star, I think. Yeah, one. All these other things are actually galaxies, and they're really far away. And so this is another way that we can know what was going on way back in the universe's history. We can know that by just looking farther.
Yeah, it's kind of cool because we get like a look back in time.
Yeah.
We saw everything as it is now.
I don't recommend it, but if you look at the sun, you're not seeing the sun as it exists right now. You're seeing it as it existed 8 minutes ago. Because the sun's so far away, it's about 100 million miles, it takes 8 minutes for the sun's light to reach us. So when that light reaches us, it's been emitting more light for the subsequent 8 minutes, and so we don't see that light until 8 minutes later. And when you look at stars at night, those stars are usually a dozen, 100 light years away, which means you're seeing those stars that they existed hundreds of years ago. When you look at galaxies, you're looking at millions of years ago or billions of years ago. The farthest galaxies go all the way back to nearly at the beginning of the universe. So we can literally look back in time just by looking farther and farther out. You get better telescopes, you can look farther back, and you can start looking back in time to start checking your predictions as to what was going on then.
Well, yeah, because if you could see where the universe originated, wouldn't you see the Big Bang?
Well, that's the thing. Right after the Big Bang, the universe was not transparent. So the light that was being emitted then will never reach us. It wasn't able to, yeah. But we do see the afterglow. This pattern right here, the microwave background radiation, that is essentially the afterglow of the Big Bang, right when the universe became transparent. That light starts permeating the universe. That light, again, predicted by the Big Bang model before it was observed. And then we observed it, and we're like, oh yeah, that Big Bang is probably onto something. Right? There's a lot more evidence in today's world. So anyway, you go back far enough and there's no galaxies. You just got a bunch of stars with a lot of gravitational potential energy. But then they start grouping up with stars that are close by a relative term. They start grouping up with stars that are close by, creating the first galaxies. This is a spiral galaxy kind of like ours. I think this is Andromeda. It's kind of like our galaxy. We don't get pictures of our galaxy because we're within it. And we sent the Voyager spacecraft out at the fastest speed that humans have ever sent anything out. And it's still barely at the edge of the solar system. And that was in the 70s, right? So there's not a chance that we'll ever get outside of the Milky Way galaxy to get a picture of it. But this is the Andromeda Galaxy, I think, and we're actually on a collision course with it. The Milky Way will collide with the Andromeda Galaxy very soon, in about 4 billion years. And here's the Sombrero Galaxy. It's pretty. So these are all, when these stars, they're just chilling out there, but then they start taking that gravitational potential energy and converting it to kinetic energy. And so now these giant galaxies, all the stars orbit the central black hole at the center, and they have a lot of kinetic energy that they derive from that initial gravitational potential energy. Sometimes galaxies can take that gravitational potential energy and actually convert it to kinetic energy as they come in and collide. And one of my favorite videos...
You probably wouldn't survive that.
Actually, you probably would.
We would?
Yeah.
Really?
So this is a cool video. It's a computer simulation of two galaxies colliding. And again, the Milky Way is going to collide with the Andromeda Galaxy. The collision itself will probably happen over a period of several hundred million, if not over 1 billion years. Yeah.
I'm like a programmer or something, and I learned that whenever galaxies collide, there's not like any much collision between stars and crap because of how big they are.
Yeah.
It's like almost no change. We wouldn't notice.
Yeah. We would notice the night sky getting very dramatic. It would look very pretty. But the chances that our solar system would be perturbed by the collision is probably pretty small. So you can have collisions between two galaxies, and like Alex says, with two galaxies with 1 trillion stars in them. And chances are that no two stars are going to actually collide in that collision. Yeah.
So they're just kind of like going to go through each other.
Yeah, and that's what this simulation will actually show. Right? You have these, and not only that, but it'll stop the simulation and then show a photo that Hubble has taken of two galaxies in that stage of collision. So check that out. It's pretty cool. Again, these collisions take place over hundreds of millions, if not billions of years. Like that picture of these two galaxies about to collide, you go back to the dawn of human civilization and look at that same setup, it looks exactly the same. It hasn't changed at all. Because it takes such a long time for these things to happen. Oh yeah. So this is the simulation. They start to, again, no stars, as Alex pointed out, no stars are colliding here. It's just the gravitational interactions, the gravitational energy converting to kinetic, but then they just kind of pass through the space between them. And that's because stars, yeah, they're huge, but the spaces between them are vastly larger than the size of even the largest star. And then you get the kinetic energy of the stars that kind of flings them out in these tail shapes. Very pretty. And then they kind of, if they're gravitationally bound to each other, then they'll kind of orbit. They'll kind of pass through each other and like orbit, go back and forth.
And do the two black holes merge?
Yes. That's the collision that will happen between any galaxy collision. The central supermassive black holes will always collide and form the core of the new galaxy. So again, there's the simulation.
So if we were closer,
there's an actual picture.
If we were closer to the center, we might get pulled in.
If you're closer to the center, there might be radiation concerns.
Like if it's a larger mass, the gravitational pull would be stronger, right? So
yeah, but still, the black holes are not as nearly as dangerous as people think they are. Okay.
It's just something with more mass in a smaller space. Like if you turn the sun into a black hole, nothing would change.
Yeah.
We would die because we didn't have the light.
Okay, so that's galaxy collisions. The largest galaxies in the universe are elliptical galaxies. They don't have the spiral shape. It's not entirely understood as to why. Some scientists just think they don't have the angular momentum that's required to make the spiral shape. But some are probably formed just by a bunch of galaxy collisions over billions of years. Those galaxies can get very large. This is a picture of our galaxy, the Milky Way, and then the largest galaxy that we know of. And the Milky Way is not a lightweight. It's over 100,000 light years across. It has probably 3 to 400 billion stars in it. This guy's got trillions. Yeah. Anyway, so now let's actually start focusing a little more on energy. I like teaching astronomy when I can because astronomy's cool. But now let's talk about the energy. Turns out our solar system and all the solar systems formed from giant gas clouds. You might have learned about that in middle or elementary school. So you have this giant gas cloud and by giant I mean larger than your brain can even comprehend. Giant gas cloud that gets triggered somehow into a gravitational collapse. So this particle here has gravitational potential energy relative to this particle here, right? They want to come together. And so if something triggers that, then they can end up starting to come together. And so later on in the history, you might see something like this. These are actually, most people look at this picture and they think this is the empty space, the dark areas. No, that's where the matter is dense. That's where the gases are most dense. This is actually, there's a bunch of giant blue stars. Like if you look higher up in this picture, giant, very high energy output blue stars. They're pumping tons of radiation down. They kind of create a wake. These are like wakes. That's why it has that shape. And they call these the pillars of creation. This photo is called the pillars of creation because these little nodules, if you look closely, like they're like a rock in a stream, and you see the water flowing around them. Well, those little nodules are actually solar systems being formed. Those are gas clouds collapsing and starting initiating the process of solar system formation. So you have a bunch of gravitational potential energy, right? This is all about energy. Gravitational potential energy in this gas cloud, and then that gravitational potential energy starts converting to kinetic energy as the gas cloud collapses into what will become a solar system. This is a photo of an actual solar system actively being formed, right? And even the planet, you can see where the planets are going to be, because you have right here where you see these dark bands. Well, that's because the matter has been sucked up by something that's orbiting around it and is accreting that matter and probably going to become a planet. So not only is that gravitational potential energy converting to kinetic energy, but this is gas we're talking about. So what happens to gas as you go from a very large volume to a very small volume relatively? It heats up. And so the temperature starts climbing. It goes real big. And eventually you're going to get so much matter right in the middle there, it's going to form this big ball of gas. And once that gravitational potential energy has converted into enough thermal energy, it initiates the process of, anyone know? Nuclear fusion. Which, this is a very simplified diagram of nuclear fusion, what actually happens. You start with two hydrogens. Once the temperatures are reached, the temperatures and pressures required to reach, they get forced, this is the process of work, they get forced together. They get forced together until they actually collide. These are positively charged particles. They don't want to come together. They want to repel. But if the pressures are high enough, then the thermal pressure will force them together doing work, right? And then they collide. One, through a decay process, becomes a neutron. A positron gets spat out. That's what conservation of charge, right? We still need to have two positive charges. So you spit out a positron, which is a positive electron, essentially, and a neutrino, which is another subatomic particle. And then that heavy hydrogen, which is a hydrogen and a neutron, or a proton and a neutron, collides with another free hydrogen atom. And then when they collide, it becomes a helium atom, and it spits out a gamma ray. That's light. It spits out a particle of light. That happens here. That also happens down here. And then the two helium-3 nuclei collide together to produce a helium-4 nuclei, and then two hydrogens just get spat out to undergo this process again. So this is what's going on inside the sun. The energy that we get from the sun are these gamma rays. Right? Those gamma rays come to us from the sun, carrying energy that is liberated in the nuclear, from the nuclear potential energy in this process. Okay. So yeah. By the way, the sun burns about 700 million tons of hydrogen every second, and will do so for 10 billion years. Right? That's how big the sun is. That's how much fuel it's got. But where does the energy come from? Well, it turns out that if you add the masses of these four hydrogens and compare it to the masses of the other and these two hydrogens you can just think of as these ones. They came in after the fact. But you compare the mass of the hydrogens to start and the helium nuclei afterward, the mass of the hydrogens before is more than the mass of the helium nuclei that gets spat out at the end. Now, it's not a conversion process. You'll usually hear people say that mass is converted to energy, but it's more complicated than that. But essentially, you take the mass and you liberate it in the form of electromagnetic radiation via an equation that you might have heard about. Yeah. That's talking about nuclear processes. Nuclear fusion, nuclear fission. It's not the full equation. if the particles are actually in motion, which they are, there's a more complicated equation, but if the particles are at rest, then it simplifies to this. Notice c is the speed of light. That's a very large number, so a very small amount of mass can produce a very large amount of energy. There. But the sun takes about 700 million tons of this and converts it to about like 690 million tons of this every second of its existence, on average. And then those photons leave the center of the sun, do what's called a random walk as they go from the center of the sun to the outside of the sun, to the surface of the sun. They constantly get reabsorbed and re-emitted and reabsorbed and re-emitted by all the particles within the sun. This process can take up to 1 million years. Statistically, it might take 10,000 years to 1 million years for a photon to get from the center of the sun to the surface. And then it takes 8 minutes for that particle of light to get from the sun to the earth. Very little of the radiation put out by the sun actually hits the earth, right? Earth is very tiny in comparison to the sphere of influence of the sun. But remember, this is energy that was derived from the gravitational potential energy of the gas cloud that converted to the thermal energy that initiated the nuclear process that liberated the energy in the form of nuclear radiation, or through the process of nuclear reactions that formed the light, which carries energy away from the sun. That energy then comes to the earth. You didn't hear that. Comes to the earth. And this is the earth as it looked during the Carboniferous era. It was about 250 to 300 million years ago. You've probably heard of Pangaea, Gondwana, or Gondwanaland. This is what the earth looked like then. They call it the Carboniferous period because the earth's surface was covered by Carboniferous material, i.e. plants, a lot of plants. Very tropical. The entire world was pretty much tropical. The configuration of the continents, they were all together and then surrounded by a vast ocean. That happens in Earth's history quite a bit. The continents separate and then they come together. It's happened 4 or 5 times in Earth's history, 3 or 4 times. But in this time, they call it the Carboniferous because the Earth looked like this. All right, this is when you had this is before dinosaurs even, but this is like when you had giant bugs and it's really boggy and gross and stinky and swampy, but very, very conducive to vegetative life. And so you have all this vegetative life that ends up dying eventually, and then in certain environmental conditions, the vegetative life dies. It could be in the oceans, it could be on shore, and then it gets buried. And climate can change based on the tectonics of the earth, and so all this stuff might die and then get buried by sandstone or something like that. Might get buried by different sands or silts, and eventually enough of that stuff can bury it so that the weight of the material ends up lithifying or creating rock out of what was initially like sand or silt or stuff like that. And then tectonics can cause those rock layers to move, and this is what geologists do, petroleum geologists. They actually try to figure out where in the subsurface you have these, they call them anticlinal patterns of the rocks. And any oil that's produced because of the dead vegetative matter, that's what fossil fuels are, right? What's the fossils? It's dead plants, a little bit dead animals. The energy that they get from the sun through photosynthesis, they produce biological energy. Well, dead things still have energy, right? When you burn firewood, that's a dead tree, still got its energy. When you burn it, you still get the flame from it, you get the heat. That energy comes from the sun originally, because the sunlight is what allowed that plant to grow. Well, when the plants die, they still got energy, and for the right environmental conditions, they can be converted to oil or natural gas or coal. And in the right geologic conditions, that oil can condense into reservoirs that we can then drill down and pull the oil out, and we can refine the oil, and we can put it in our gas tanks, in our cars. And then your car engine, huge number of energy conversion processes. You take that oil, you refine it into gas so it's flammable, and now you got chemical potential energy that was originally in the plants, that is now in the oil. And then you refine it, and then you stick it into this little chamber here with your fuel injectors, which don't inject liquid fuel, by the way. Like, liquid fuel does not get burned. You put liquid fuel in your car, but the fuel injectors put gaseous gasoline into the chamber here. And then your spark plug, if you ever wondered what spark plugs are for, they literally spark an explosion, a little mini explosion with the gas. and you liberate that chemical energy. That chemical energy then becomes thermal energy, because so when it becomes thermal energy, you heat up the gas. What happens to gas whenever you heat it up in a tiny chamber? It expands. It creates pressure. That pressure then exerts a force on the piston, and that piston moves over a certain distance. So the expanding gas does work on the piston, giving it linear kinetic energy. The piston is then connected to the crankshaft, so the linear kinetic energy of the piston gets converted to the rotational kinetic energy of the crankshaft, which is connected via the drivetrain to your tires and gets your tires to spin. So, long story short, the energy that was originally gravitational potential energy in the gas cloud that formed our solar system got converted to the thermal energy as the solar system got compact and the sun got hot, which then liberated nuclear potential energy in the form of gamma rays, which then left the sun in the form of light, which then grew plants, giving them biological energy, which we then tap into 300 million years later. Right? That they call it the Carboniferous period because the vast majority of oil deposits in the world were formed then. Oil still gets formed naturally, but it's like this classroom. Fill this classroom with oil. That's how much oil the Earth produces in a year in today's world. But during the Carboniferous era, it was massive, massive. And so that energy we then liberate by igniting it and taking that chemical energy, converting it to thermal energy, which then gets converted to linear kinetic, rotational kinetic, gets your tires to spin. This is a picture of pistons in an actual engine. And as one goes down, the other one goes up, so it's like a cyclic process, you know. And then it makes your car go. My car. And then you get to school today. So literally the energy that you used to get to school today was originated in the gravitational potential energy of the giant gas cloud that then formed our solar system, which is pretty cool. Now, any physics teacher worth their salt will tell you that at least some of the stuff that they told you today is not true. We said that before about the gravitational force, right? So it turns out that, and her theorem actually predicts this. Over the entire course of the history of the universe, energy has not been conserved. There's actually more energy in the universe now than there was at the beginning of the universe. And that's because of this dark energy. The universe is expanding, but the dark energy density contained within space itself is not changing. So if the density isn't changing, but the universe is getting larger, there's more energy than there was before. But, and Noether's, however you say her name, her theorem predicts this though. Because her theorem says there must be a symmetry, a spatial symmetry. There is spatial symmetry on small time scales. And by small time scales, I mean tens of millions or hundreds of millions or maybe even a billion or 2 years. But over the entire age of the universe, that symmetry is broken, and therefore the conservation law gets broken. So, but on our time scales, for the entirety of human existence, energy has been conserved. So in this class, we talk about energy as being a conserved quantity, meaning it doesn't change. Total energy doesn't change.
Isn't that why the scientists were like, hey, let's introduce antimatter and dark matter into this?
Kinda. Remember to watch those videos, guys. Do that quiz.